classes on fundamentals of electrical engineering. We had moved into electric machines, wherein we discussed DC machines first, and then we moved on to transformers, both single phase and three phase, as also auto transformers. And now the natural progression happens to be induction machines, essentially induction motors. Though EMF kind of relationship, as also the induced EMF kind of relationship, as also the equivalent circuits are more or less very similar. The major aspect of difference happens to be the fact that induction machines are rotary in nature, and when they're rotary in nature, all the different aspects of with respect to the rotary nature come into the picture. Like for instance, there is what is called as the most important aspect happens to be that the motor delivers a torque, unlike a generator or a transformer. So in this context, we'll be learning mostly about torque, as also how the induction motor creates a rotating magnetic field, and then thereafter the rotor tries to run behind the rotating magnetic field and does not succeed entirely. So we have first and foremost what is the synchronous speed. So of course the relationship is very similar, very popular. It is given by 120 F by P, where F refers to the frequency of the stator supply and P refers to the total number of poles that are created in the stator. Then we also have the slip. As I said earlier, the slip happens to be what is the difference between that gives the difference between the speed of the rotor as well as when compared to the stator magnetic field, the rotating magnetic field. Okay, of course, this is there is always a slip. Otherwise, if they catch on, then they are locked together, and then we are having synchronous speed, and we don't have an induction motor thereafter. So we have the slip given by ns minus n, where n is the actual speed of the rotor divided by ns, which is the synchronous speed, and that speed refers to the rotating magnetic field, or it is not a physical kind of speed. Okay? So we also have, as was mentioned earlier, a very important aspect of torque being delivered, and of course the torque equation is derived, but we need it only to the extent that we can say that the torque is given by 3 times, because of the 3 phases involved there, multiplied by 60 by 2 pi ns, where ns refers to the synchronous speed, not the actual speed, but the synchronous speed. And then we have the slip s multiplied by e2 square, where the rotor voltages refer to the stator or the primary. Okay, when you're talking about a transformer, okay, multiplied by r2. Okay, to get the power factor. So we have R2 divided by square root of R2 square plus S square X2 square, because the frequency is different. So we are having S into X2, where R2 and X2 refer to the resistance, as also the reactance of the motor when referred to the stator. Okay, so we also have the current being given by E2 divided by the square root of R2 square plus S square X2 square. So in total, torque is given by 3 divided by 2, 3 into 60 divided by 2 pi ns multiplied by S into E2 square into R2 divided by R2 square plus S square X2 square. Okay, so this is one formula that we need to remember. Okay, so this is what we will be using soon enough. Some of the theory is being covered through the different questions that we have for gate examination. So let's start with the first question. Okay, a 3-phase 4-pole squirrel cage. Okay, so there are 2 types of motors. Of course, I'm not taking a class on motors, just the fundamentals, but of course we have 2 types of motors. One is a squirrel cage kind of induction motor, of course 3-phase induction motor, and then we also have what are called as the wound type. Okay, so and they are called a slip ring induction motor, because the power is fed to a slip ring. Okay, so then in the question, a 3-phase 4-pole squirrel cage induction motor has 36 stator and 28 rotor slots. Okay, so through the slots we have the conductor moving. Okay, the number of phases in the rotors. Okay, so it's always going to be a 3-phase machine, so you will always have 3 phase. Okay, so option A is right, though we are given several options. Please remember that whatever is given to the stator is going to be induced in the rotor, so we are having a 3-phase there. Okay, so moving to the next question. The slip of an induction motor normally does not depend on. Okay, so what is the slip? As I mentioned earlier, slip is given by certain relationships, where first and foremost we discuss ns as equal to 120 F by P. Then what is n? N is given by ns into 1 minus s. Okay, just a reorganization of the so all these, and moreover torque is given by, as I said earlier, 3 into 60 divided by 2 pi ns S into E2 square R2 divided by R2 square plus S square X2 square. So let's see, is the slip of an induction motor dependent on rotor speed? Of course it is, okay, because slip is given by Ns minus N divided by Ns, okay. So N happens to be the rotor speed, okay. Synchronous speed, yes, that relationship also comes. Shaft torque, yes, because torque is now proportional to, as I said earlier, it's proportional to, via the equation, proportional to S, okay, or proportional to 1 by S depending upon the speed of operation, okay. And then of course core loss component, no, it's not dependent on the core loss component. Core loss component depend upon the voltage, and that is square, okay. Let's move to the third question. For a linear electromagnetic circuit, the following statement is true, okay. Okay, so there are 4 statements. Let's read the statements. Field energy is equal to the co-energy. So there's a diagram given there where co-energy is, okay, it's a plot between I and lambda, where lambda happens to be the flux linkage, okay. So we can see that the co-energy will be given by the area under the line, okay, or under the curve, okay. So how do you assess that? You always have a value for lambda multiplied by di, and then you integrate it, okay. So lambda has to be expressed in terms of I. So in the linear zone, it can be given, or it can be the same as equal to mi, where m happens to be the slope. So you see that I square is going to come into the picture, okay, something like half Li square, etc. So we have the co-energy same as the field energy, okay. So it's equal to the co-energy, okay. Field energy is greater than, okay, so that's something different. Field energy is lesser than, no, field energy is equal to the co-energy, okay. Co-energy is 0, no, co-energy cannot be 0, okay. Moving on to the fourth problem, okay, depending upon the diagram that is given alongside, okay. So now let's look at the fourth question. What does it tell us? It tells us that the directional rotation of a 3-phase induction motor is clockwise when it is supplied with 3-phase sinusoidal voltage having phase sequence ABC. So this is the general phase sequence, okay. For counterclockwise rotation, that's also possible. What do? You just take 2 phases and interchange them, okay. So the counterclockwise happens, and so phase sequence has changed, okay. So what becomes the phase sequence? It can't be ABC or BCA or nothing like that. There should be an exchange, okay. So we see that BCA is the same as ABC. If you continue to read it becomes ABC, 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 ABC. Next is again ABC, because it is CAB, CAB, CABC. So you can see that it's the same. The third one, that is C, happens to be ACB. Now there is an exchange, okay. So ACB is right. We don't need to go further, okay. So yeah, so these are all general, very general, as also basic kind of things, okay. So fifth one, leakage flux in an induction motor is, what is leakage flux? It's always that what links with one winding and does not link with the other, okay. This is applicable to transformers, it's applicable to induction motor as well, okay. So this is where things match, okay. So of the 4 options, obviously D tells us that flux links the stator winding or the rotor winding, but does not, okay. And what does not link will not create what we want, like torque, etc. That's why it's called as a leakage flux, okay. In the sixth one, in an induction motor, if the air gap is increased, what happens when the air gap is increased? Okay, so of course we see that the reluctance increases, okay. So obviously we have, okay, so let's read the answers. Speed will reduce? No, there is no chance of speed reducing just because the air gap is increased. Efficiency will improve? No, efficiency will actually go down. Okay, power factor will be lower. This is the reason, this is what is happening, okay. This is what is happening. Why? Because we see that the magnetization, it draws a larger magnetization current, okay, because the air gap is increased, the reluctance is more, so it draws a larger magnetization current, which means that the inductance content is going to be, inductive content in the current is going to be larger, which means that the power factor is going to be poorer, okay. And the last one is breakdown torque will reduce. No, let's see, look at the breakdown torque. Breakdown torque is the maximum torque, okay. And we, of course, this in the diagram we have shown 3 different modes of operation. One is the constant torque operation, and other is the constant power operation. Third is, of course, where we don't go, which is the breakdown torque operation. This is also what is called as a pull-out torque, okay. It's the maximum torque, okay. So in all these cases we may have a maximum torque, okay, which is not utilized because then the machine will pull out. Okay, moving on to the 7th problem. Under no load conditions, if the applied voltage to induction motor is reduced from the rated voltage to half the rated value. So this is dangerous, okay, because when the voltage comes down, okay, what happens is that that the machine does not perform appropriately. Even in our homes, we can see that even single phase induction motor, when the voltage comes down, the speed reduces. It starts to no, it's not actually crawling, but it starts to go very slow. So the speed comes down, and also the stator current also, because the voltage is reduced, the stator current, the current that is pulled from the voltage, pulled from the source, becomes smaller, because the voltage supplying is lower. Okay, so both the speed and the stator current decreases. Okay, these are very simple things. Moreover, the torque relation at no load. Okay, please remember this is a no load condition. So torque at no load is proportional to S. It's not proportional to 1 by S, because the speed is larger. So S is proportional to S. It's also proportional to V square. So S tells us that, that if the torque is maintained constant, the speed goes down. Okay, and then because if the torque is proportional to V square, the voltage has gone down. That's the reason why speed goes down. Okay, and of course, since the voltage has gone up, the current also goes down. Okay, so different ways of explaining the same thing. Okay, eighth problem or eighth question: a rotating electrical machine having its self inductance of both the stator and the rotor winding, independent of the rotor position, will definitely not develop. Okay, immediately when they are dependent on each other, that is, the stator and the rotor windings are dependent on each other. This is the situation when we are having the salient pole kind of machine. Okay, in that case, we have what is called as a reluctance torque. Okay, so in this case, reluctance torque will not develop, because they are not, the self inductance of both the stator and the rotor windings are independent of the rotor positions. Okay, of course, it will definitely develop starting torque, it will develop synchronizing torque, it will also develop hysteresis torque. Okay, so reluctance torque is normally due to two axes. One is what is called as the direct axis, and another is called as the quadrature axis, and then they are dependent on each other. Okay, so then we have what is called as a reluctance torque. Okay. Yeah, ninth question: a balanced three-phase voltage is applied to a star-connected induction motor, the phase to neutral voltage being V. Okay, the stator resistance, rotor resistance refer to the stator, stator leakage reactance, rotor leakage reactance refer to the stator, and the magnetizing reactances are denoted by RS stator, RR rotor resistance, and then again RS, RR, XS, XR. Okay, so it's given as XS, XR, and then again XM. XM is the magnetizing reactance. Okay, which is shunt, which is in a shunt manner. The rest are all series in nature. Okay, just like an auto transformer, just like a transformer's equivalent circuit. The magnitude of the starting current of the rotor is given by, now S is equal to 1, so it's very easily the same as equal to the voltage, applied voltage, divided by the impedance. Okay, total impedance. Okay, and there S does not appear, so we have R. The shunt will not matter at all. The shunt winding, the shunt kind of existence of the magnetizing reactance will not matter. So it's simply V divided by square root of RS plus RR whole square plus XS plus XR whole square. There's no S, because at starting, that's what is asked, slip is equal to 1. Okay. Yeah, because ns minus 0 divided by ns. At starting, n is equal to 0. The machine has not yet started. Okay. The 10th question, we have a diagram. So what does the diagram tell us? The diagram tells us that it's like a torque slip characteristic or torque speed characteristic. Yeah, that's what is written. And it says different zones. Okay, there is a negative speed zone. Okay, we also have what is called as a we also have a negative torque. Okay, negative torque means it is absorbing power. Okay, on the torque speed curve of the induction motor shown in figure, 4 points of operations are marked as W, X, Y, and Z, which we saw. Which one of them represents the operation at a slip greater than 1? When does a motor operate with slip greater than 1? Okay, only when ns minus ns has ns minus n divided by ns. That's the slip. Okay, so for it to be greater than 1, the speed has to be in the reverse directions, or it should rotate in the opposite direction. So it becomes ns minus minus n. Okay, then it becomes ns plus n divided by ns. Okay, so obviously the negative speed zone is when W is marked. Okay, so the answer is W. Okay, as simple as that. Okay. You come to the last slide. So far we have not discussed problem. Now we'll be discussing two important problems, the 11th one and the 12th one. Okay. A star connected. Okay, star connected means the phase value is going to be by root 3. Okay, so all the ideas that we had when we were discussing transformers can be now borrowed here. Okay, so a star connected 12.5 kilowatt 208 line. Okay, so it's star, so 208 by root 3 is going to be the voltage if required, 3 phase 60 hertz. Okay, so it's not 50 hertz, 60 hertz. Please take notice of each of these things. Okay, squirrel cage induction motor has following equivalent circuit parameters. Okay, we were discussing so far about equivalent circuit parameters, RS, etc. Okay, per phase refer to the stator. Okay, R1. Okay, that's the stator resistance 0.3 ohms. Then rotor referred to the stator is R2 is equal to 0.3 ohms. X1 again stator side 0.41. X2 referred to the rotor reactance referred to the leakage reactance. Okay, referred to the stator is X2 is also is equal to 0.41. Neglect shunt branch. Okay, of course, as we usual, the shunt branch has a large reactance, so it's normally it will take very little current, so it's not taken into consideration normally. Okay, so let's see what the question is. The starting current. Okay, starting current means S is equal to 1. Okay, for this motor when connected to an 80 volt. Okay, so the voltage has reduced 20 hertz. The frequency has reduced 3-phase AC source. Okay, so now earlier it was 208 volt as the line voltage. Now it has gone down to 80 volt. Okay, so at that time, we are having so we are given the reactances etc measured when we had a higher voltage and a higher frequency. Okay, so all those aspects need to be taken into consideration. So how do you calculate the per phase current? Okay, so it's per phase current which is flowing through each of these stator winding. Okay, so we have 80 divided by root 3. I suppose it's clear. It's a line voltage, so 80 divided by root 3 divided by the impedance. What do we have? We have 0.3 plus 0.3, that's the resistance component, so 0.6 square. Then we are having 0.41 plus 0.41, that is 0.82, but then 0.82 is applicable to 60 hertz. So you divide by 60, multiply by the new frequency, which is going to be equal to 20. Okay, so 0.82 divided by 60 into 20 is equal to 0.273. So 0.273. Very simple square. Okay, very simple. But the two ideas that need to be remembered happens to be that the per phase currents are going to be the currents that are flowing through the stator windings. Okay, each of the three stator windings. So we have 80 divided by root 3 as the available voltage now. Okay, and when the starting current is flowing. Okay, so what does the starting current face? It faces both the resistances. Okay, so because the primary resistance, the rotor resistance has been brought forward to the stator, so we are having 0.3 into 2 or 0.6 square. Okay, it also has the reactance, but the reactance is changing. Why is it changing? Because the frequency has changed. Okay, so we have 0.82, both of them together, divided by 60, multiplied by 20, giving us 0.273. That also can be squared and added. There's no slip here. Why? Because S is equal to 1. It's a starting current which is being asked. Okay, so that portion you have to be very careful about. Okay, last problem, the last question in this session. Here we are having a delta connected. Earlier it was star connected, delta connected. Okay, so phase values are applicable. Okay, 3.7 kilowatt, 400 volt line. So 400 volt line voltage is the same as the phase voltage for the delta connected motor. The 4-pole 50 hertz squirrel cage induction motor has the following equivalent circuit parameters per phase. Okay, normally they'll be giving only per phase. Okay, that's all that's possible. Okay, refer to the stator. R1 is equal to 5.39. R2 is equal to 5.72. You can add them together, okay, if required. X1 and X2 are same, 8.22. So into 2. Okay, so when they come to the stator side, neglect shunt branch as in the earlier problem in the equivalent circuit. The starting line current, so it's the same in amperes, rounded off to 2 decimal places when it is connected to 100 volt. Okay, again line. So earlier it was 400, now it is 100 volt. Okay, 10 hertz. Okay, so again frequency has moved on from 50 to 10. Okay, 3-phase AC source. The same kind of problem. Okay, this is one aspect with respect to the electrical machines. Most of the problems are repeated. Okay, so we can easily the first step is to calculate the new reactance. How much is it? 8.22 into 2, that is 16.44 divided by 50 multiplied by 10, which is equal to a particular 3.288. Okay, so 3.2888. So we have 100 divided by, there is no root 3. Why? Because it's a phase voltage. Okay, so 100 divided by square root of 11.121, that is 5.39 plus 5.72, whole square it, and then we are having 3.288 square. So that gives us the phase current. Now multiplied by root 3, you see that that's going to be the line current which is drawn from the supply. Okay, so that's all that's there. I suppose some general aspects were discussed. Okay, mostly the fact that three-phase begets three-phase. If you give a three-phase rotating magnetic field to the stator by giving a three-phase power supply, you get three-phase on the rotor as well. Rotor can be either in a squirrel cage construction manner, or you can have the wound type. Okay, then you'll have the slip ring kind of thing. Okay, then of course they are short circuited either through a resistance for the wound type. Here of course they are through the end rings. Okay, the construction is important. It's good to remember what are the components. Okay, then we are having what is called as the applied voltage, that is the three phase voltage which is applied to the stator creates what is called as a rotating magnetic field, and the rotor because the rotor is short circuited, it has EMF induced in it, and it runs a current. So there's flux and the current interacting with each other, and so the motor starts to rotate. Okay, it will always try to catch up with the rotating magnetic field. It will never catch up. So there's a slip. Okay, so that slip is an important aspect which we'll be discussing in the next session in almost all problems. Okay, then we also realize that this is the way that the shaft will take on the load. Okay, and as the load increases, more and more current is going to be drawn. Okay, but there are different types of currents that are drawn. One is the starting current, and now is the full load current. Then of course we also have perhaps no load current. Okay, so there are the other different load currents as well. Okay, so mostly no load current, starting current, as also as also full load current. Okay, and then the machine can deliver maximum torque, it can deliver starting torque, it can deliver torque at different loads including the full load. Okay, so all these possibilities are there, but the starting point is very, very important. We have the one of the difficult areas with respect to induction motor is the large starting current drawn. Why? Because slip is equal to 1. Okay, when it's starting. Okay, so so we have what are called as some starting techniques also coming in the further sessions. Okay, thank you.